All right, so hello, everybody over there, and welcome to my presentation. Well, my name is Aldo Teran. I recently started as a PhD student, but I was working already as a research engineer in several projects. So I'm just gonna pick up where I left off last presentation I had in these seminars. So we're gonna talk a little bit about the R2Sonic 2020, the multi-beam echo sounder that we mounted on Lolo, a bit more about the calibration and the deployment, the full integration we did on Lolo, the results as well, some verification of those. And then I'm gonna jump to another project that I'm working on right now, which is self-docking with mobile docking stations, also with Lolo. And let's jump straight to it then. So this is where we left off kind of last time. We did an integration of the multi-beam on Lolo, and we did a harbor calibration, they call it, that we mounted it and we used total stations to measure the offsets and everything. And then we got that into the computer inside Lolo that we call a scientist. And we went out to do some more tests. So we did what is called the patch test for multi-beam echo sounders, which is a sea trial calibration, which is standard for survey vessels. That normally what you do is 4 different tests to compensate the offsets, the mounting offsets for roll, pitch, and heading. And well, for roll, basically is the one that you see here. It's just basically going in a straight line back and forth and computing that roll offset that you will have on your multi-beam. Oh, this is really bright. And we did it for roll, pitch, and heading, and we also do it for latency between the localization, or the GPS localization, and the data, the incoming data from the multi-beam. And we didn't get a lot of successful results on the pitch and heading because of the GPS inaccuracies that we have in Lolo. We don't have RTK GPS, so it tends to jump around a little bit. So when we tried to compensate for pitch and heading, we couldn't overlap the map precisely to do the patch test, basically. But here you can see the roll test that it was the one that worked successfully. And what you basically do is you overlay both lines, the way and the back survey lines that you do with the vessel, with the multi-beam, and you extract a patch, a vertical patch on the data. And then this is the vertical cut that we do there, but you just put it on 2 dimensions. And basically you look for the roll offset, which is this one, and then you compensate for it, which we only have like 0.3, 0.4 degrees, which doesn't look like much, but when you're mapping at 200 meters depth, that it's quite, you can see the errors then. So we did it. We did it successfully for the roll. Pitch and heading, well, it was a little bit more complicated, but we couldn't do much with our current setup. But then, well, we went out and did a longer survey with Lolo. And, well, it's sensitive information, so it doesn't have like the mission. There's no geo-reference data here, but it was somewhere. And we mapped like an underwater feature that you can see here. And this is the raw point cloud of a lawnmower pattern we did. Something like this with Lolo. It had several lines, and we wanted some overlap, of course. We missed some areas here, but Lolo is a little bit temperamental sometimes. But here on the edges of the feature, we got some noise over here, which is reflections from the vertical features that when the multi-beam tries to do like bottom lock, well, bottom extraction, there are some settings that you can change in order for it to know that there are vertical features and it doesn't do this kind of errors. But we got them there, and well, we just had to filter them out. So what we basically did was grab all those noisy areas, we built a mask, and we took them off the whole data set, and this is how it looks cleaner. Of course, we have some data here missing now, but that is still right. And this map also has computed normals, estimated normals, so you can see a little bit of more how more like the 3D view of the whole area. But this is still pretty good data. And then what we wanted to do, well, what we were tasked to do was to verify that we had done a correct integration of the multibeam on Lolo. So we had to compare this with some ground truth data. So MMT has a survey vessel called Ask Coleman, and they did measurements of this area we were around before, and we got those measurements, and that's this mesh that you see here on the background. That's the MMT data, which is from a survey vessel, which they use for professional use. So it's pretty accurate. And what we basically did was use the coordinates of the points that we got from Lolo, and we overlapped it on their map, built a bounding box, and extracted that whole patch to compare exactly our data with theirs. And here on the left, you see the point cloud from the MMT data, and this is Lolo's point cloud over here. There are some black spots there, which is wrongly estimated normals of some points, but those get filtered out once you build a mesh. And the respective meshes are here. So this is the MMT mesh computed from that point cloud, and this is Lolo's mesh computed from that point cloud. And of course, we had to downsample it a little bit, so because we had so many points there. But qualitatively, it kind of looks similar. Of course, you have some interpolation due to the method that I'm using to build a mesh. You have some interpolation here on the bottom on both maps, and here on the top on both maps as well. And of course, those missing pieces of the point cloud from Lolo that the MMT map does have, those were also interpolated like here and here, as you can see. But then there's pretty nice qualitative results. But then we run it through some mesh comparison software, and we got some numerical results, which these are probably new. No one else has seen them because I did them recently. And we, as you can see from the mesh, like the general mesh that we got in Lolo without the interpolated parts that were on the top and here on the bottom, white means almost like no difference, and blue means that it's deeper, and red means that it's higher, the comparison. But in reality, if you see the distribution, the mean difference that we have is minus 0.4 centimeters, which actually corresponds to the difference that we have from the IMU in Lolo, which is our reference point for all of our data, to the waterline. So that's a constant offset that I haven't really added to the transformation tree on Lolo. So she doesn't know about that offset. She thinks that the IMU is at the bottom line, at the waterline. So this means that we were kind of in the center of at zero difference from the MMT mesh, which is pretty amazing. Pretty happy about it. And yeah, I think that's it about it. Oh yeah, this is the same image, but with colors, if you were missing the colors. All right, and yeah, of course, this is the contour map that everybody likes the bathymetry contour maps. And on the top, you see the MMT from the Ascolmen, and you see Lolos now here, which look pretty similar. You saw the difference in the other one. And yeah, so for future work with the multibeam, well, all of these steps that I showed you before, we want Lolo to do them automatically, of course. And that's something we're leaving for the future. And we also can get backscatter information from the multibeam. And we want to use that, but we have to calibrate it, of course. And we can also use the multibeam with different frequencies. So we can have a multispectral configuration on the multibeam, which we haven't actually developed the software for it, but it's there. And with that, we want to do some area detection and classification of seagrass that some people really love. And then also with Nacho, with Ignacio from RPL, we've been looking at using the multibeam to do terrain-aided localization using a particle filter. But maybe he'll talk about that on next sessions. But all right, that was it for multibeam stuff. So this is another project that I've been working on. This is soft docking with mobile docking stations. And it's optical soft docking, we call it, because we're gonna rely on visual sensors, optical sensors, to do the soft docking maneuver. Okay, but the entire project consists on 3 different phases. One is the recall and the rendezvous. So imagine that Lolo is underwater in a remote place. So it's going around in a mission in this remote phase, and then it has to come back to her mothership or the submarine where she left off from. So when she comes into the recall phase, into recall distance or rendezvous distance, then the submarine or the docking station or whatever can send a USBL sign, a USBL message or some kind of acoustic message to tell Lolo, like, okay, it's time to go home, get here to this spot at this time and have this course and this speed or whatever, and we're gonna pick you up. And we are at this place, so hurry up. So then Lolo will follow instructions and go and plan a trajectory, follow that trajectory, and enter the rendezvous and the soft docking phase. Once Lolo is in front of the submarine where she's supposed to be, at the speed that she's supposed to be, we want to have an optical leash on the submarine or the docking station. This means that the docking station is going to be signaled by light beacons around the docking station that are going to help Lolo pinpoint the position of the docking station and also aid her into estimating correctly her attitude towards the docking station, which this is really important. And then the soft docking part is, well, it's similar to orbital station keeping that spacecrafts do with other spacecrafts, that they're just following the same, they have always the same position towards each other, independent or how they're moving in space. And that's what this soft docking is. Then the last phase is hard docking, but this project is not going to involve the hard docking part. So we're not actually going to go inside. We just have to get through the station keeping part. But throughout this, all these 3 maneuvers, Lolo really has to know what she's doing with respect to the submarine. So this is the approach we want to take, is to estimate Lolo's trajectory using a Postslam representation. And Postslam is basically doing using factor graphs to estimate Lolo's pose. And we have these 2 phases, the recall and rendezvous. where the only contact we have with the docking station or the submarine is via USBL. So we have these USBL constraints on our graph. Oh, maybe I should explain a little bit of this first. X1, X2, X3, these are Lolo poses. The red dots are the dead reckoning of Lolo. Blue dots are constraints that are given through the USBL from the submarine, which is L1, L2, L3. And the docking station is, of course, on the submarine, so these green dots are just the rigid transformation between the USBL position to the docking station, to the center of the light beacons in the docking station. So that's a known. These are known, and this is measured at reckoning, and this is measured USBL. And then when we make first contact with the submarine, we have an idea of what the submarine, where the submarine is, where is it going, and how is it getting there. So we can propagate the state of the submarine and put that in Lolo's belief system or in her graph, and we can optimize over that. And
sorry, is this like a state diagram, and each dot will contain information that relates the circles to each other?
Yeah. So this is it's a graphical, probabilistic graphical representation.
You highlighted like what
of
instrument, what method would like.
Yeah, this is just a measurement. Actually, it's like range and varying from the submarine to Lolo's USBL antenna. So then you can optimize over that using some sort of solver. And
L1, what was L1? What's L or inside?
Oh, L is the submarine. It's a landmark. It's just
the submarine.
Yeah, this is the submarine. L is the submarine.
Okay, DS is the docking
station. X is DS is docking station. Yeah. Okay. X is Lolo's
position.
State.
Yeah. Okay,
yeah. And then we go to the optical leash once we are in range of the docking station and we have visual contact to the light beacons. Then we add this factor here that is just a measurement of the relative position between Lolo's camera and the center of the docking station that is estimated through light beacons. And here, as you can see, well, the good thing about using like the visual feedback is that it's so much faster than getting USBL data. So, for example, here we don't have a USBL measurement, but we can still estimate the position of the submarine and the docking station using the camera, the optical leash. Yeah, so then you put this in a solver and you estimate as best as you can Lolo's pose throughout the whole soft docking maneuver. I'm so scared of touching it now.
Why did you get why did you get the USBL back?
Because it's just a different rate. You don't lose it,
okay,
but this is just running so much faster than the blue one. So, these are some preliminary results from a student I've been working with, doing his master thesis. And he's looking at the optical leash problem while designing the docking station, the light beacon displacement, and doing a lot of signal processing, image processing, and finding the center of the light beacons, and then estimating the pose of the docking station. So what he's basically doing is providing this factor that you saw on the past graph, is the relative pose between Lolo's camera and the docking station. And well, here you can see how he began. Well, his approach is to use 5 different lights, 4 in a square in a planar surface, coplanar points, and then 1 outside of this coplanar plane. And well, he has done it on simulation. He did it on the surface with some LEDs, small LEDs, and he just recently went out to do some field tests, and these are some of the results that he has gotten. Here you can see how he successfully finds the center of the lights and then computes the image, the pose, I'm sorry, and you can see also, this is not meant to be here, but these are meant to be here. So these are outliers, so sometimes you get reflections from the surface that you might probably not get super deep where a submarine is supposed to do, but it's nice to see that it's robust. And you can see how he computes the position of the docking station. It's pretty cool. And well, yeah, the next steps are, so we have to verify the whole pipeline first. So it's hard if we don't have the platforms to experiment, to do these whole experiments right now. So I've been setting up a simulator. Well, I was setting up a simulator on the gazebo before, but I was recently told that Stonefish is pretty nice, and it is pretty nice. I haven't used it before. So I want to verify the performance in first off ideal conditions, so no noise on the image on the water or anything. And what Stonefish is pretty cool about is that you can actually make the water more turbid and add particles and stuff like that. So that's it's pretty cool. So first I want to verify that everything works in this simulator and maybe derive some noise model for the camera or something useful for the field experiments. And then we have to prepare some platforms. Well, we have Lolo's working. Lolo has a USBL there, but now we have to build some kind of contraption with the light beacons and put the USBL topside unit there to pretend that it's a submarine, and then put it on the buster or on the boat or on the kayak or whatever, and run some field experiments. So it's pretty cool. This is an image of the simulated camera on the back of Lolo. You can see the propellers and the fins there. Very nice. But I think that's about it. Yeah. Thank you.